Hey y'all, welcome back to Math Rescue. I'm Andre, a certified math coach. In this video, we're going to analyze a real-world polynomial model and break down all of its key features: domain and range, extrema, end behavior, intercepts, and even symmetry. I'll show you how each of these connects to what's actually happening in the situation the model represents. So, the math starts to tell a real story. Let's talk about it. So we are working with a model of coral fish population in the coastal bay. X is going to represent time. It's going to represent specifically the amount of years that have passed since 2000. And f of x, aka the y-axis, is going to represent the actual fish population in thousands. We have the algebraic rule represented here. And we are also given the graphical representation of this model. They're both saying the same thing, just kind of saying it in different ways. The idea of multiple representation is super important in high school algebra. It helps us to understand the calculations that we're doing a lot better. So let's first start with describing the key features of this function. And then from there, we'll kind of talk about what it means in terms of these coral fish. So let's start with our x-intercepts. I can see that we have two x-intercepts. Now this grid is on a scale of 50. I can see 50 on here. So I'm thinking that these are all 10. This would be 20, 30, 40. Yeah, so it looks like we have an x-intercept at 30, 0. It also looks like we have an x-intercept, kind of going back here a little bit, maybe 3. Since this first line right here is going to represent 10. -3. All right, next up, let's look at our y-intercept. So we only have one y-intercept right here. Our y-intercept is at 20. So I'm going to say 0, 20. Right. Let's mark our extrema. So Desmos is wonderful. Desmos does a really nice job of putting gray dots that you can click on anywhere where there might be a point of interest. In this case, they've gone ahead and put dots on our two relative maximums and our relative minimum. This maximum here is actually not a relative maximum. This is actually absolute max. There's no y value higher than that, and we're going to talk about what that means for our coastal fish in a second. So let me go ahead and record our extrema. So we have a maximum near, I want to say that's maybe x equals 3. And the y value there, it looks like 10, 20, 30, not quite 30. So I'll probably say 28. All right, for our minimum, we will say that it's happening at 7. And it's just a little bit lower than the max. So I'll say 26. And then I'm just going to put a little note right here that we have an absolute max at, and I actually went ahead, when I was on Desmos, I actually clicked on this one, so it gave me the exact values. So this is at x equals about 23, and y is at about 88. Right. Next up, let's look at our domain and range. So for polynomials, domain is always going to be all real numbers. However, since this is a real world model, I want to take a time to think about this in terms of the real world. My domain probably won't make too much sense to be negative, especially if I don't have data that predates the year 2000. And I'm also not going to have data that's crossing into the future. I'm going to kind of cut this off here at x equals 0. And so we'll just say that x is greater than or equal to 0. And I can see that either the population died down here or, well, this is 10, 20, 30. This is like 2030. So maybe they're just predicting that the population is going to end in 2030. All right, let's look at the range. So for the range, I can see that my y values are less than, this is the wrong symbol here. My y values are less than or equal to this maximum that we have up here. So my y values are less than or equal to 88.45. And I'm just going to go ahead and round it. Y could be anything less than that. All right, for my end behavior. So as x is approaching negative infinity on the x is the left side. And our other notation says as x approaches positive infinity, that's going to be referring to the right side. And I want to know what's happening to our y values. F of x is just notation for saying y, vertical axis. So it looks like on the left side, the end behavior is going down. And it looks like on the right side, the end behavior is also going. So I'll go ahead and I'll denote both of those with negative infinity. Okay. That was all the analysis. However, we still haven't really talked about what this means for the fish population. So year 2000, let me kind of clear up some of the writing I have on the graph here. Year 2000's data is happening exactly right here. This is year 2000's data. So at year 2000, the population is at 20,000 fish. In the first 10 years, so from the year 2000 over to this first line, in the first 10 years, it looks like the population increases about 10,000 with a slight kind of dip here and a slight peak here. Maybe that was the ecosystem balancing itself out. Maybe this was a fish population that was artificially brought into an ecosystem, so it kind of peaked and then something affected it and it kind of dipped back down. But we're predicting that after about 23 years, the population is going to hit some type of peak right around 90,000 fish. That is a whole lot of fish. And then from there, something's going to happen, and there's going to be a massive decline in the population, all the way to where by the time we get to 2030, we are not going to have any fish left. Maybe that's because they predict there's going to be some type of climate crisis. Maybe we don't expect the ecosystem to last past that point. I'm not sure. But we are able to kind of extract all this information from the graph. And Desmos is really nice for turning a kind of ugly algebraic rule into a really nice visual for data. So in this case, for doing something like this, looking at a situation like this, the graphical representation is definitely ideal. I'm Andre with Math Rescue. See you next time.